channel. So for today we are going to discuss about the Fajan's rule. Okay, this is actually related to the covalent character of ionic bond. So what is actually Fajan's rule? Okay, it is actually used to predict the whether the chemical bond will be covalent or ionic. Okay, and actually depend on the size of the cation and also anion, and also the charge of this cation and also anion, right? So for this Fajan's rules, okay, or more to what we call polarization, this is what we have learned previously, the dipole moment and also bond polarity. Okay, so for the polarization to be or will be increased, okay, it is actually depends on three factors. Okay, first one is the high charge and small size of the cation. So it is actually the charge is the Z, okay, plus over size, radius, okay, radius, okay, and so this will give us what we call polarizing power. Okay, second factor other than cation is second one is anion. Okay, we need to have high charge and large size of the anion. Well, you know, if you have higher charge or high charge of cation, you will be having small size of cation, and if you have a higher charge of anion, you will be having a large size of anion. So this polarizability of an anion is actually related to the deformability of its electron clouds. Okay, and then the third one, we need to have an incomplete valence shell electron configuration. So if we have a noble gas configuration of the cation, we will be having better shielding and less polarization, less polarizing power. Okay, so the charge factor in number one, okay, based on the cation. So this one, it is actually related to the effective nuclear charge or Z effective. Okay, alright. So for example here we have mercury 2+. The radius is 102 picometer, and it is more polarizing than the calcium 2+, because of the radius of the cations is radius of the calcium 2+ here is 100 picometer. Okay, alright. So here, alright, so this Fajan's rule actually was formulated by the Polish bond chemist Casimir Fajan in 1923, or between 1923 to 1924, and these rules actually govern the degree of nonpolar character, or we call it as covalency, present in ionic compounds. So we want to be able to predict, okay, the compound, whether it is actually ionic or polar. Okay, so the theory for these rules actually, the bonding in these compounds is purely ionic, and so what happened here, it is actually attraction between positive and also negative ions. So the electrons on the negative ion, or we call it as anion, can also be attracted towards the positive ion. Okay, because we have different charge here. So what happened here, it will start to distorting the shape of the anion, and also resulting in a degree of covalency, or what we call here is electron sharing. So here in this diagram, okay, So this is an idealized ionic bond where we have the positive cation and also negative anion. So this is the size of the cation is much more smaller than the anion. Okay, because we have different charges, okay, here positive and also negative, and this positive cation has tendency to attract electrons surrounding the anions. Okay, so what happened here, this anion is polarized. Okay, so we have a movement of electron cloud. Okay, so what happened here, the cation, okay, is slightly polarized and they will show some covalent character. Okay, so when this distortion of electron cloud happen, okay, so what happened here, anion and also cation are both polarized and they will have covalent bond in this structure. Okay, so the Linus Pauling dealt with variation of or variation in polarity in terms of the degree of ionic character in covalent bonds. Okay, while for the Fajan here, he discussed the variation in the degree of non-polar or covalent character or covalency in ionic compounds in terms of polarization effects. So the polarization effects or movement of electron clouds between anion and also cation. Okay, and Fajan's rules focus on size and charge relationship, the size and also charge of relationship, and second one, electronic configuration of the cation. Okay, so the charge density here, where we have the charge over size. Okay, this is the charge, okay, positive or negative, and also the size, okay, the radius. And for the size, we have two ions here, cation and also anion. First one, for cation, this non-polar or we call it as covalent character increases, okay, with decreasing cation size or increasing cation charge. Okay, so we need to have a smaller size here. Okay, size. So when you have a smaller size, so what happened to the charge? Usually the charge will be increasing. Okay, right. So very small cations or cations with high charge density usually tend to distort or polarize the electron cloud around the anion. Okay, so here the greater the polarization of the anion, the more non-polar or covalent bond between the atoms. Okay, second one, okay, so we need to have small size and increasing cation charge. Okay, and second one, we need to have a bigger size of anion. Okay, size here, and a bigger anion charge. Okay, alright. So when we have big size and also the charge also increase, okay, so what happened here? Okay, it is more easily to polarize, okay, by cations because we have large electron cloud and because of the electrons are held more loosely. Okay, right. So the bigger the size, the smaller the attraction between the nucleus and also electron surrounding the anion. Okay, so here this is the summary, okay, of the Fajan's rule. So we have two important factors here. We need to have the size, okay, small cation and high charge. So we'll have highly polarizing, okay, and then the anion must be large and also has high charge. So it is actually highly polarizable, while for the cation is highly polarizing. Okay, so here, okay, we have non-polar covalent character of the non-noble gas configuration, then the noble gas type cations. Okay, so cations with 8 electron structures cause less distortion or less polarizable, and they undergo less distortion and than those with the 18 electron structures. This is, we call it as pseudo noble gas structure. Okay, how do you want to know the pseudo noble gas structures? Usually they will be having the electron configuration of n-1 with the d10. Okay, with the d10. For example, copper. We have example for copper, and then we have indium. Okay, and so on. So they are having pseudo noble gas structures or pseudo noble gas electron configuration. Okay, so in this example here, we have copper 1 and also sodium. Okay, sodium ion here. Okay, this copper 1 has the electron configuration of Ar3d10, where we call it as pseudo noble gas configuration, while for the sodium plus here, this is the noble gas configuration. Okay, as you can see from these values of the size. Okay, this sodium has 0.95 angstrom, while for the copper plus is 0.96 angstrom. So the number of protons of sodium is 11, while for the copper is 29, and size and charge are almost the same. Okay, but okay, let's say we have an anion. Okay, an anion that near the copper ion compared to the sodium ion. Okay, behaves as though it were under influence of a greater ionic charge and distorted to a greater extent. Okay, alright, and then what happened here, the spherical field of the d electron cloud is more easily polarized by anions than is an 8 electron shell in sodium. Okay, so this one in sodium. Alright, so this result in some polarization of a pseudo noble gas cation by the anion. Okay, and so from this example, okay, we have more polarizing power of the copper plus. Okay, why? Because increase in effective nuclear charge. Okay, so in periodic table, this is the sodium in group 1, while for the copper, okay, it is actually situated in D or transition metal. Okay, so this copper has higher or more polarizing power. Okay, if we have an ion, okay, let's say this is an ion. Okay, more power compared to this sodium. Okay, why? Right, because of the pseudo. Configuration, while this one we have noble gas configuration. Okay, right, while this one we have the Ne electron configuration, and while for the copper we have D10. Okay, we have the Ar3D10. Okay, so this is more polarizable. Sorry, this is more polarizing than this sodium. Alright, and then other than that, we have covalent characteristic. Okay, these physical properties of ionic compounds such as melting point, boiling point, the conductivity, the solubility, and etc. actually are affected by the covalency of ionic bonds. Okay, so here we have a few examples. Okay, Fajan describes that the covalency increases when we have let's say when the covalency increases, the solubility decreases and the melting point also decreases, okay, because of the compound is become more covalent, okay, right, compared to the ionic compound, okay, which has higher solubility and higher melting point, okay. So here we have magnesium sulfide and also magnesium oxide, okay. The covalent character increase with increase of size of the anion, okay. So if you see the position of the sulfur and also oxygen in the periodic table, sulfur is much more bigger than the oxygen, okay. So when this here, this is based on the size, size. So when we have larger size of anion, so more covalent character in that compound. So magnesium sulfide is less soluble than the magnesium oxide. So for the second example, this is also based on the size, but decrease of size of cation. For the first one, we have increase of size for the anion, and second one, decrease of size of the cation. So we need to have a smaller size of cation in order to have higher covalent character in that compound. So the here decreased size of cation, beryllium, okay, so we have beryllium chloride and also calcium chloride, okay, and this is totally ionic compound, okay. This is totally ionic compound because we have group 2 calcium chloride with the chlorine here, okay, compared to the beryllium dichloride here, where it has a much more lower melting point compared to the calcium chloride, okay. And then Fajan also described as covalent character increases with increasing charge on either ion. So we need to have higher charge of cation and also higher charge of anion, so they will give us a smaller size and also a bigger size of anion, okay. So here, for example, we have iron 3 hydroxide and also iron 2 hydroxide, okay. So iron 3 here has higher charge, so the size of the iron 3 is much more smaller compared to the iron 2, because one Fe3 plus and another one is Fe2 plus, okay. So we remove 3 electrons from here, and while for this one we remove 2 electrons, okay. And then there's higher covalent character, alright, in iron 3, okay. And then another example here, we have covalent character in greater for cation with a non-noble gas configuration, okay. So transition metals are generally less soluble than those alkali and also alkaline earth metal, group 1 and also group 2, okay. Why? Because of the size, and also here in this case we have an example in terms of melting point of mercury dichloride and also calcium chloride, mercury chloride and also calcium chloride. So mercury chloride we have 276 degrees C compared to the calcium chloride 772 degrees C. Okay, so the mercury chloride here is much more or less soluble compared to the calcium chloride. Okay, alright. Why? Because one here we have pseudo, or this is non-noble gas electron configuration, while for this one we have a noble gas electron configuration. And then the conclusion for the Fajan's rule here, First thing, if we have a given cation, covalent character increases with increasing anion size. And for a given anion, okay, covalent character increases with decreasing cation size. The third one, okay, covalent character increases with increasing charge on either ion. Okay, it's actually reflect the point number 1 and also point number 2. And covalent character is greater for cations with non-noble gas electron configuration. Okay, alright, and then this is actually related to the point number 4. Okay, and so as usual, okay, we have example. Okay, predict which is more covalent. Okay, I have a few 8 example. So we will discuss this example during our virtual class tomorrow. And then last but not least, I have a question here. Which of the following is least covalent? So this also we will discuss in the class, and please do this example, do this question A, B, C and also D with justification. Okay, alright. Which one is the least covalent, or in easiest way is we call it as more ionic. Okay, yeah, that's all for today for the Fajan's rule. This is actually related to the last week lesson. Okay, so guys, I'll see you guys in the next video. So that's all for today. Hope you guys enjoy this video, and please don't forget to like, comment and also subscribe my YouTube channel. So I'll see you guys in the next video. Bye.